Four coordinate compounds. Yeah, four coordinate compounds. Let's talk about this tetrahedral square planar. So tetrahedral complexes possess only optical isomers, no plane of symmetry. This is a tetrahedral. So there is no plane of symmetry. So they are only optical isomers. If you put them in front of the mirror, you can find a different image of them. So it means you make another compound. Square planar complexes rarely exhibit optical activity. These are the square planar. You can see 2 chlorine, 2 nitrogen, and to the copper center, square planar. So they don't have like mostly no optical activity because they possess plane of symmetry, Racemic mixture, when a certain solution contains equal amounts of levo and dextro isomers, 50-50, said to be optically inactive. We call it racemic mixture when there is a levo and dextro, which they have sharing 50-50 each one of them, the solution said to be optically inactive, not active, one cancel each other. Essential condition for compound to be optical active is asymmetry, plane, asymmetry. So levo and dextro, you can see here. So this is the levo, this is the dextro structure. Okay, two compounds. Isomer is molecule that can build in two ways, left-handed version and right-handed. The atoms are all the same. Two isomers are mirror image to each other. When you pass polarized light through a solution containing an isomer, it will change its polarization slightly, either to the left or to the right, depending on which version of the isomer is in the solution. If polarization changes to left, it will be levo isomer. If changed to the right, it will be dextro. So it's all in solution. So tartaric acid occurs naturally in many plants, particularly grapes, bananas, tamarinds, commonly combined with baking soda to function as a leaving agent in recipes. It has a good ability to rotate polarized light. And again, this is like industrial application when they use tartaric acid to add it to the food or something. So they will change to the light and the solution will be in a different color. In enantiomers, non-superimposed mirror image, non-superimposed. So if you bring this, okay, superimposed is this one. This is the superimposed. Two hands superimposed. And they are mirror to each other. Imposed. But if you change like this, so these are not superimposed. They are mirror, but not superimposed. So superimposed, all molecules, atoms, position will be the same. As you see here, you can put this one on the top of this one, not top, like with this one. You can see this atom will be to the left and the similar atom to the right. So it's a structure, it's a mirror image, but we call them chiral structures, but they are not superimposed mirror image. So if they are not superimposed, it means they are enantiomer. enantiomers here as well, you can see, you can put this on the top of this, and this, the two reds will be to the right, the two reds to the left, so they are not superimposed. As you see here, we can put the mirror image and the mirror in the middle. So again, these two compounds, they are similar formula, but position are different, okay? And they are not superimposed, they are enantiomers. Stereoisomers have same atom bonded to each other, but different optical or spatial arrangement. This or diastereoisomers, they are geometrical isomers. We call them diastereo, not mirror image and non-superimposable. Enantiomers, mirror image, but not superimposable. So again, it's like we are talking about different meanings. If you come to the diastereo isomers or stereomers, you can see here two amino group in the cisplatin, and here in the cis, and here in the trans. So now you can see these are diastereomers. It's like a stereo. Diastereomers have different chemical and physical properties, of course. Different color, melting point, polarities, solubilities, chemical reactivities, but the optical isomers also have different properties. Of example, nicotine in tobacco is very toxic, naturally occurring, while D-nicotine prepared in laboratory, non-toxic. Okay, there is I-nicotine, there is D-nicotine as well. So these are diastereomers. Enantiomers, mirror image, and you can see another example. If you, these are not or non-superimposed, if you, and they are mirror image to each other, like cis and dichloro diethylene diamine or bis ethylene diamine, cobalt 3 and iron. This is a cis. So this is the cis, one beside one, neighboring, two chlorine atom, and we have ethylene diamine, two groups. It's octahedral. There is a mirror image, but not superimposed. They are enantiomers. And more you have here enantiomers, different position. You have a non-superimposed as well, as I said. Look at these two. They are cis, but these two groups, it's ethylene diamine, but it's been rotated. Like, so this, because of this, is not similar to this, so they are not superimposed enantiomers. Now, summary knowledge, you can see, state the type of isomerism may be exhibited by the following complexes. And I have the answer beside them. So if you just draw this, you can find oxalate, and you have, this is octahedral, so you can differentiate hydration, because the hydration, it's a water molecule inside the complex bonded directly to the chrome. You can say this is hydrated. Sometimes the isomer, you can read it both in two types of isomer in the same formula. Okay, so give the oxidation state of the metal and DN configuration for each of the following. So here was the oxidation number for the manganese. You can say 6 minuses. Difference from the 4 minuses will be 2. 2 minuses, manganese will be manganese 2. Difference between 4 and 2, 2. So iron will be 2. different, or Cl, pyridine is neutral, Cl is -3, so cobalt will be 3, and so on. Identify the compound if they have an isomer. So if you can check cobalt, bis-ethylene diamine dichloro, if square planar, no isomer. If tetrahedral, isomers. So when you draw the structure, you will find the answer here. And now you have there is a square planar, or you have here the same ligands. Wherever you put them, they are the same. So there is no isomer for this. Here you have NO2. So NO2 is ONO or NO2. It's a linkage. And here you have polarization isomer. There is a polarity. Here there is a linkage as well, because from the N side, and you have ionization because of the bromine. So this as well could come as draw the isomerism scheme. So either structural isomer or stereoisomers. Structural will be ionization, hydration, coordination, linkage, polymerization. And stereo will be geometrical isomer or optical isomers. Definitions, I put here as a definition for each one of them, depend on the what. It's a structural but hydration. There is water. Structural coordination. So there is a linkage. There is everything here is like definition in a brief. Okay, so this is the end of the isomerism.